Solar energy has been available since the day the sun first lit up. Humans have also been trying to harness this solar energy ever since we realized its potential. Nature has captured solar energy for eons, long before humans picked up on its energy potential. The process of photosynthesis has long taken solar energy and converted it into glucose for use in plant cells. In the 7th century BC, it was first discovered that a glass could concentrate the sun's power and start a fire. In the 2nd century, the Greek scientist Archimedes used mirrors to start fires on enemy ships. Though little proof of this feat exists, the Greek Navy attempted to recreate it in 1973 and managed to burn a wooden ship 50 meters offshore. The Swiss scientist Horace de Saussure built a solar collector in 1767, which Sir John Herschel used in the 1830s to cook food on his South African expedition. In 1839, the French scientist Edmond Becquerel discovers the photovoltaic effect. His experiment consisted of an electrolytic cell made up of 2 metal electrodes placed in an electricity-conducting solution. He found that electricity generation increased when exposed to light. In the 1960s, French mathematician Auguste Mouchet came up with the idea of a solar-powered engine. He and his assistant built the first solar-powered engines that were the predecessors of modern solar-powered panels. A company called Hoffman Electrics developed 8% efficient photovoltaic cells in 1957 and a 9% efficient cell a year later. In the next 4 years, Hoffman continues to increase the efficiency of the cells and discovers how to use a grid contact, which greatly reduces the resistance of the cell. In 1965, Peter Glaser proposes the idea of a solar-powered satellite. In the 1970s, the U.S. investigates the idea of solar energy satellites. The project was a $20 million investment, but amounted to nothing. The technology was not available at the time to truly understand solar power to its full potential. In 2000, the International Space Station had solar panels installed on a massive solar satellite in space. The solar array has wings of 32,800 cells each. This solar satellite may be primitive and costly, but it is the precursor for modern improved satellites.
But how do we convert solar energy into usable energy? Currently, solar panels are used to harness the sun's energy. Solar panels use a process called the photovoltaic effect to convert sunlight into usable energy. Solar cells are made of semiconductors such as silicon. When light strikes the cell, a portion of it is absorbed in the semiconductor. The energy from the absorbed light is called a photon, which knocks electrons loose, allowing them to flow freely. The PV cell has one or more electric fields that direct the electrons in a certain current flow. Metal is placed at the top and bottom of a PV cell to draw the current for external use. The current produced is direct current power. DC power flows electrons in a single direction. An inverter converts the DC power into alternating current power. To convert from DC power to AC, the DC current hits a magnet that activates and pulls a wire spring to contact the current. This will change the flow of current to the other side of the circuit. Once the magnet is released, the spring will snap the wire back, allowing the current to flow back to the other side of the circuit. The AC power can move currents both forward and back. This allows for energy to be transferred from the solar panel to the electric grid, and also from the electric grid to the solar panel. This two-way flow of electricity can be very beneficial if the building with the solar panel is producing more energy than it is using. AC power is also able to alternate between higher and lower voltage levels. High voltage levels allow energy to be transmitted at longer distances. Conversion from DC power to AC allows the energy to be used in homes because it is safer to transfer over long distances and provides more power. There are many benefits to solar energy. By harnessing just 1/4 of solar energy that comes to Earth, it would be possible to meet the Earth's energy needs comfortably and then some. Depleting fossil fuels such as natural gas, oil, and coal would also be spared by using solar energy, as it is currently an unlimited resource. Solar energy would also allow the United States to be less dependent on foreign oil and fossil fuels. In a 2008 analysis, 60% of U.S. oil was foreign. Currently, oil and coal power plants produce pollutants such as carbon dioxide, nitrous oxide, and dust. These pollutants lead to global warming and smog. Coal generates 54% of U.S. electricity, but is also the biggest air pollutant. Solar energy would reduce pollution significantly. The solar panels do not give off any pollutants. The only pollution from solar energy is during the manufacturing of the solar cells. A study shows that even with the pollution from the manufacturing of the solar panels, pollution would still be decreased by 90% when using solar energy.
However, if solar energy sounds so promising, why isn't it used more often?
The first and possibly the biggest problem with solar energy is the cost. An average set of rooftop panels costs $20,000 to $30,000 and takes 10 to 15 years to produce enough electricity to pay for itself. This is why many people are not willing to give them a try. The cost of solar panels in comparison to other forms of energy is very large. The next problem facing solar energy is its efficiency. In the 20th century, only the wealthiest people were using solar power. This only made up for 1% of all energy. Currently, a typical commercial solar cell has the efficiency of 15%, meaning only 1/6 of the sunlight hitting the panel is turned into energy. Although this percentage seems low, it is 11% higher than when solar panels were first created. Also, when looking at renewable energy as a whole, it only makes up 7% of all U.S. energy needs. We would like to see this percentage increase. Also, the materials needed to make solar panels are not only expensive but sometimes out of reach. In the past, there have been silicone shortages. The process of producing pure silicone becomes a problem. In 2011, there was a shortage in silicone wafers because many of the factories that produced them were wiped out by natural disasters. Problems like this make it hard to consistently depend on solar energy. Lastly, a more obvious problem dealing with the efficiency of solar panels is that solar energy is only accessible when the sun is out. Therefore, it cannot be used at night and even on some days when the weather is not permitting. This is where the idea of a solar satellite would be very beneficial.
A solution to increase energy production from solar energy is the use of solar satellites. Solar satellites harness more energy from light in space because on Earth, the air in the sky absorbs most of the light energy before the rays get to the solar panel. People see the sky as blue because red and green light rays are absorbed or reflected by the air and allow the blue light to pass through. In space, solar panels would absorb much more energy because there would not be anything absorbing the light rays in between the panels and the sun. Another benefit of being in space would be that the satellites would have a longer period of time in sunlight than the panels on the Earth's surface. The process of how solar satellites work start with the solar panel's photovoltaic cells. The cells convert sunlight into electrical current, which then powers a microwave generator. The microwave generator then beams microwaves down to a collection point on the surface. The collection points would then gather microwaves and convert the energy back to electrical current. The microwaves would be at 1 gigawatt strength and would have about the same radiation as the leakage of a microwave oven, and would not be harmful to humans, wildlife, and weather patterns. Another step that was thought about was putting the satellite at 36,000 kilometers above the equator. At that point, the solar satellite would be at geosynchronous altitude, which would then take 24 hours to orbit, so that means the satellite would almost be stationary relative to a point on the surface. The shortfalls of the solar satellite, though, is the size of the thing and how to get it into space. Each panel is 10 kilometers wide, and the microwave transmitter is 1 kilometer wide. The transportation of these materials into space would take more than a few trips, and each trip into space costs $450 million, which results in billions of dollars used to put one solar satellite into orbit. Another issue is that the system would only power about 300,000 homes. Clearly, there are still problems to address regarding the solar satellite, such as its size and cost, but we believe that it would be worth it in the long run. To decrease the number of trips, the solar satellite could be sent up in pieces in combination with other space projects. As for cost, the solar satellite could pay for itself over time. 300,000 homes is a relatively small number compared to the global population, but with improvements in capturing the sun's energy, we hope to see this number steadily rise.